About HDFS scalability and its evolution. In particular, the recently merged in HDDS and Ozone, as I'll explain in the talk, that has been merged into the Hadoop as a sub-project of Hadoop. So a little bit about myself. I am Chief Architect Founder at HortonWorks, an Apache Hadoop PMC and committer since the early days of Hadoop when it was created at Yahoo. Prior to that, I've worked in data center automation, virtualization, Java, etc. at Sun Microsystems, a startup, and also at Inria, a PhD from Waterloo. My partner in crime, in fact, he deserves more credit for this work than I do. He's the lead developer of Ozone HDDS at HortonWorks. He's also obviously an Apache Hadoop PMC member and committer. Prior to that, he was a part of the founding team that created Windows Azure. Unfortunately, he could not be here today to co-present with me. So I'm going to kind of give you a quick overview of what does Hadoop do well, not do well, and then talk about how we approach to scaling it, which is one of the key limitations today in HDFS, and then some details about the project. So what HDFS is very well. It's the best at scaling I/O bandwidth, petabytes, and number of clients. Okay, you can horizontally scale I/O and petabytes by just simply adding data nodes. Okay, you have very fast I/O scans and writes. Number of concurrent clients is in the order of 60,000 plus. Maybe it's much more now, right now. So you have very large clusters of thousands of cores, tens of thousands of cores that are bombarding a single name node. It has fault-tolerant storage lower. You can remove a data node. You can add a data node. A disk can fail. It just takes care of itself. It gives you locality in the sense that you can move computation to where the storage is. And actually, if I have some time at the end, I'll kind of talk a little bit about the myth of that HDFS must require for you to put compute on storage, and it does not allow segregated. So if I have some time, I'll touch on that at the end. It's a myth, actually. And that there is a mostly clean layering of namespace layer and storage layer. Not quite. It has a security system that integrates well with Yarn or a system where you are submitting jobs and executing, and the client is no longer there to authenticate. One of the limitations of HDFS is that it's limited to 500 million files. And the reason for that is that it keeps the namespace in memory. It also is a limitation of scaling the block space, block reports, scaling data nodes, block management. The block scaling is actually much better than the files. And there are some customers who say they want to go to beyond 60,000 concurrent clients. They want to go to like over $150,000 to $200,000, where it may. What is actually kind of people say, why were you guys so stupid to keep the namespace in memory? ext for all the file systems, keep a working set in memory, keep some inodes in memory. Well, it turns out namespace in memory is actually one of the strengths of HDFS and also one of its weaknesses. Strength in the sense that that's one of the reasons why it scales to so many concurrent clients. A lot of competitors have kind of created a similar system, whether it's from a vendor and they actually cannot scale to a large number of clients. So this is one of the strengths. In fact, this was part of the original design at Google, and we kind of used that as our first implementation. We wanted to kind of move towards just caching the working set in memory. We actually did a prototype on that with a student from CMU a couple of years ago, and you'll see kind of that work come in here. Okay, so this is one of the, was one of the strengths, and ironically, sometimes the strength is also a weakness when you go beyond what it was designed for. Okay, proof points that there are large HDFS clusters. There are single organizations that have over 600 petabytes on HDFS. No other system actually can claim that, except probably the one inside Google. Single clusters with over 200 petabytes in a single cluster using federation. Large cluster with over 4,000 multi-core nodes bombarding a single name node. Federation is the current scaling, sorry, typo there, for both namespace and operations. It's in deployment Twitter, slight variation of it in Yahoo, and a backport of it in Facebook and elsewhere, okay? So I'm going to now talk about how do we scale HDFS. I'm going to talk about a new piece of technology that we built called HDDS. I'll explain what that is, and Ozone. As I start that, I'm going to kind of explain the layering in HDFS. So there are actually two layers in HDFS today. There's the namespace layer on the top and the block storage layer on the bottom. And the block storage layer has a library that is inside the name node. So for example, the block management part of the block storage layer is inside the name node. It's a library. Now, it turns out that there are some violations of this layering that we did. And that has been one of the pain points in separating it out. But it is mostly well done. There are some violations that could be worked around, okay? There's a lock and there's some few things, but it can be done. So I'm going to bear this layering in mind. This layering continues in the new system, but much cleaner. And we'll talk about what to do. So again, as I mentioned, there's the namespace layer and the blocks layer, okay? So how would you scale the namespace layer? Several options. If you're using a hierarchical file system like HDFS, most important one, okay, is, for example, you could cache only the working set in memory. I'm not talking about, so basically, if a large system, you might be storing data over 5 years, but most of the time you're accessing data in the last 3 months or last year, which is, a smaller portion. So you should just cache that working set. But you do need a little bit of extra memory because you're occasionally going to say, okay, let me run a query and see if this observation that I see happening today and happening 3 months ago, by the way, did it happen 5 years ago when I run the same query against data 5 years ago? So you do want to be able to access all your data. Okay, so you want something larger than your typical working set of whatever, 3 months, 1 year that you're accessing. So I'm not talking about taking your name node and bringing it down to 16 gigabytes. I'm talking about, in a large system, taking your name node from, say, 192 gigabytes or 128 gigabytes down to, say, 64 gigabytes, okay? That's all I'm talking about, moving down. The other thing, of course, you can do partitioning/sharding because it's a hierarchical namespace. Sharding and something is slightly difficult because you have renames and things that can happen into different part of the namespace. And so you could do a truly distributed name node, or you could do what is often called static partitioning by creating just volumes. And both are very reasonable solutions. Okay? You could actually move to a flat key value namespace and actually do some of the same things. A flat key namespace is actually easier to shard and partition because it's flat. You can use the hash function very easily, and also somewhat easier to build, and inherently maybe faster because it's a simple structure, simpler structure than a hierarchical one. Okay, how do you scale the metadata client RPC? Current name node has a global lock with a read-write. Yeah, that was actually a mistake when we did it. We thought we'd change it and code kind of sticks around and then become increasingly harder to fix. Of course, partitioning sharding would also help. Okay. And then, for example, if you cache only the working set or shard, it would help the startup of the name node. Okay. How do you scale block storage? And that is by simply saying, add a level of indirection, have a notion of blocks sit inside a container, and this would significantly and kind of have container reports instead of block reports. And this would significantly reduce the block map and would reduce the number of blocks and container reports that are there today. So the approach we have taken actually is the bottom two. We are using a flat key value namespace and the container approach. Okay. Scaling just one is not sufficient because both have certain limitations. Both have not reached the same limit, but both are limitations. So as I mentioned, we're going to go with a scalable block layer that we call Hadoop distributed data storage. Containers of blocks, a container is replicated as a group, and it reduces the block, or what we now call the container map. We scale the namespace. There's several approaches, as I mentioned, but we're going to use a flat namespace with partial namespace in memory and shard it down the road. We don't believe we need to shard it initially. Okay? Now, what happens to the hierarchical namespace? That's kind of what we are building right now, the first two blue arrows. And there is work in the community that will happen to actually take the existing name node and move it to the new block storage. Okay, so there's a Jira. People are looking at several different approaches to do it, and there's a discussion going on in there. Okay, so we're getting this first one out. And so you may ask, and I kind of come back to, well, is this flat key value namespace going to work? Aren't our apps going to just work only with hierarchical namespace? I'll come back to that. Okay, so let's see how does the picture. So today, this is the current HDFS. You have data nodes on the bottom, and your block reports get sent to the name node, and the name node keeps a map of block to IP address, and a file is a set of block IDs. Okay, so you take your block IDs, you look it up, you find the data node, that's where your data is, you go read it. Okay, that's the current structure. This is the new structure that what we have is HDDS. It has, container management, and it has the actual container storage on the data node. The data node, we can actually run these new HDDS daemons, or code, straight inside the data node. So you can actually run it in the same cluster. You can share the data node daemons, and you can also share the data node storage. So if you want to run this side by side, you don't need to fragment your disks. Okay, so that's the new model. You would send block reports from this. You'd send container reports, and you'd have a mapping of container ID to an IP address of a data node. Okay, so that's the new block layer. Okay, and what you would have is an Ozone Master on the top, very similar to the file to block ID mapping, but observe that a block ID is equal to container ID plus local ID. So you look at the container ID, map it over there, and go and access your file. Okay, so it is a very clean separation of the block layer. There is no library inside the Ozone Master to do container management or anything like that. Okay, it's in something called a container manager. Okay, down the road, we would add a hierarchical namespace instead of flat namespace. So that's how all the pieces fit together. Okay, initially, we will have HDFS as the default file system, mainly because HDFS has lots of features, okay? And we haven't got all of them ready in Ozone FS on day one, okay? So that's why you just can't replace it and say run it. And I'll kind of tell you what are the missing ones and that we plan to work on that. So you can actually initially have Ozone sit on the side, okay, as an additional namespace sharing the data nodes for applications that work with a Hadoop compatible file system on a key value store like Hive and Spark. I have a page that will explain that. And how do you access Ozone FS? So you could use direct URIs for both HDFS and Ozone FS. So that has been one of the nice things about Hadoop file system, that you can give a URI for multiple name nodes. So now for multiple files, Hadoop compatible file system. So you can just have these two and give the right URIs. So you might say I store my data for new tables in Ozone FS because I'm running out of space, and you could use those URIs to directly talk to that. And you may use your default file system, for example, because you want encryption, and Ozone FS doesn't have encryption right now, okay? Or you could do a mount in HDFS or mount into a ViewFS, okay? So you get a unified namespace view, okay? So initially that's, but down the road, you could, when we get it feature complete, there'll be people who might say, I want to move just straight to HDDS and Ozone, okay? Okay, so how does it address okay, so HD is going to be a little bit more details on that. Containers are containers of blocks. Typically, a container size is 2 gigabytes to 16 gigabytes. Okay, it is replicated as a group. Each container has a unique container ID, and every block within the container has a block ID. The name node or the Ozone Master will only store the block ID, but it turns out that the block ID is container ID plus local ID. So, for example, if I were to put this inside the old name node, it would just work because the block ID concept just stays the same. Okay? Now, 2 gigs to 16 gigs, clearly, the larger you are, the more efficient are you at scaling. Why would you just go with 16 gigs? And the reason for that is 2 reasons. One is that the larger your container size, the longer it's going to take you to replicate. And so when you, say, pull out a data node, okay, you're going to replicate every single container, every single block in it. Okay. Right now, one of the other characteristics of HDFS that a lot of people don't realize, you pull out a data node, okay, a 10 terabytes, which is old days. Now, nobody has a 10 terabyte data node. They have a 50 terabyte or 100 terabyte data node. But a 10 terabyte could be replicated anywhere from 30 seconds to maybe in the order of tens of minutes, depending on the size of the cluster, because every block in there is replicated. You do parallel recovery. Every data node is now saying blocks are missing, I'm going to send them around. And because blocks are spread out, you have parallel recovery. Compare that to RAID. You lose a terabyte disk, 24 hours, if you're lucky, 16 hours if you've got a high-performance system. Okay, this is 10 terabytes in a very fast time. So because of that, you may want to limit the size of your container. So the larger your cluster, the faster your network, the larger the block size you would use. Container size you would use, okay? We're going to start with around 2 gigabytes, get some experience, and maybe we're hoping that we could say most modern systems would work with 4 gigabytes, get some experience, and then start moving up and give some guidelines on what to do, okay? But that's kind of our initial thoughts based on some math we've done. So there's a container manager also that does cluster membership, as I kind of showed on the picture. It receives container reports from the data node, just like NameNode used to receive it, but now it's not the masters of the namespace that do it. It manages container replication. It maintains a container map, okay? And data nodes, they contain a set of containers just like they used to contain blocks. And data nodes send container reports just like they used to send block reports in the past, okay? And as I mentioned, it can, HDFS and HDDS can share the data nodes, okay? We have a concept of block pool that a lot of people are probably not familiar there in HDFS. It's a way for you to have other foreign file systems use HDFS. And that was kind of introduced when we did federation. We're going to continue with that concept so that you can have another file system. So like the hierarchical file system, we use a different block pool than the Ozone one. Or you can have multiple Ozone masters or independent Ozone systems on the same cluster if you like, okay? So just to kind of summarize, okay, we scale block management merely by the fact that we are grouping, okay? And so if you have a block size of 2 to 4 gigabytes, you're having 40 to 80x scalability and smaller map size by 40 to 80 times and a smaller number of block reports, okay? Namespace, okay, because the key value namespace that we're building caches a working set in memory, therefore it also scales very well. We don't believe we're going to need sharding for a while, but because it's a flat namespace, it's very easy to shard. Our namespace, as I'll show you in the next couple of slides, is volume name, bucket name, key, okay? Almost like S3, but slightly different, okay? And if you're interested, I can explain that later on. And so we would normally shard by bucket. And the reason for that is we want consistency of rename within a bucket, okay? So unlike S3, we are going to be consistent for renames, okay? Scaling number of metadata clients on RPC. We have no single lock, global lock, read-write lock like the name node. So we will have much, much better scaling. So you'll be able to have a multi-processor name node being able to process Hadoop RPC at a much faster rate without a global lock. Meta operations are somewhat simpler than the name node. So, and also sharding down the road would help if we wanted to go even further. Okay. Fault tolerance blocks inherits all the HDFS's block fault tolerance. You can remove data on a remover disk. We have block reports and a very similar thing. Our namespace is going to actually use RAFT rather than journal nodes. It'll make actually HA's implementation much easier and actually will give you a faster failover. Okay. And in fact, we'll let you have a standby Ozone Master actually serve out reads, for example, consistently, okay? Manageability, the fact that you don't have a GC pressure or less GC pressure, So the Ozone Master isn't overloaded, and therefore you don't have to worry about managing it, okay, and running out of space because it only caches the working set. You can specify exactly what the working set memory size you want, okay. Journal nodes disappear. RAFT actually simplifies that. Much faster startup because you're caching the working set, so you don't need to bring the whole namespace into memory. So when you're doing upgrades and things like that, you can just, the name node just comes up, clients can start using it. Initial set of clients will be slightly, get slower access as the working set gets paged in. Okay, so it helps for upgrades, it helps for failover. We don't have to do a worm failure if we don't want to, which we had to do in the old HDFS, okay? Now the question people may ask, okay, so you're going from a hierarchical namespace, you guys are all used to a hierarchical namespace in your Unix file system, and now you're going to key value, all my apps are going to fail. 2 years ago, I would say this would have been a big problem. Okay, but today, it's not a problem. Bezos, the gravity of Bezos and AWS is basically meant everybody says, I better make my application run on this. So the Hive team made sure that they worked around the limitations of S3. Okay, the Spark team has always been, in fact, trying to work first class on S3 and say that Hadoop and HDFS is stupid anyway. Okay, which isn't quite true, but they've always wanted to work on that, so they've been trying to do first class. And we now find customers are saying that they're making their apps, even if they're using HDFS, they're making sure the apps use the consistency model of S3 or Azure FS or Google File Storage. Okay, so what is missing? What is different? There are no real directories in Ozone. The fake directories, just like in S3 or Azure. Okay? ACLs are at buckets and volume level. Okay? For most people, that is good enough. Okay? If you're using something like Ranger, you can actually do much better because the security, the way ACLs are, access authorization is implemented is much more flexible. So using like a Ranger Apache project, you can actually do wildcards, things like that. Lack of eventual consistent S3 is being worked around by Hive and Spark. By the way, using something called CGuard. By the way, Ozone FS is consistent, so it does not have this lack of consistency. So you don't need to work around it. But it is being worked around just to kind of make this complete. There were various direct output committers in early versions that had issues that are being fixed. So there was a Netflix direct committer that has been actually improved significantly, and actually Netflix is moving to something called Iceberg, which eliminates the notion of commit via a rename, okay? And we at Hive has moved towards a Hive Metastore. By the way, so is DataWorks, but it's part of the proprietary version of Spark, not in the open source Spark, okay? So these apps, the key ones, are moving to make sure they work on S3-like file system, or an object store, and we will also work for it. So that's why we suddenly took the route of going with a flat namespace rather than waiting for another year to get a hierarchical namespace that also scales. But the community is working on that, as I mentioned. Okay, some details of HDDS. Okay, it runs on the data nodes. It uses, by the way, RocksDB. So it's an embedded LSM or key value store inside it. Okay, and block ID is the key inside this LSM, not to be confused with the Ozone key. And so in this picture, what it shows is that in our first implementation, what we have is in the LSM or RocksDB, each of the key each of the block ID is the key, and the value is the name of the file where the block is stored. So we are going with the exact same implementation as HDFS, that each block is a file. Okay? Now, down the road, this can be optimized in multiple ways. For example, 2 examples. If you have very, very small blocks, like let's say you decide to store photos in this instead of Hadoop data, or normally other data, you could say, let's store small blocks straight inside the LSM. Okay, so no files are needed, that would be good. A second one is, don't use one file per block. Start saying that I have a single set of files where all my blocks are stored. And so then you can start building a log structure-like file system. And that is probably the way we'll go in the next phase, okay, with also smaller files being stored in RocksDB, okay? But the first one was to get the simplest implementation. It inherits the features from the implementation of the original HDFS, okay? And so that's why we went quickly get something working that will be fast and has I/O characteristics that we do understand, okay? Now, replication of containers. This is where we wrote as part of this work on a project called RAFT, a project, I forget the name of the project now, sorry about that. It has a RAFT protocol in Java. And we use that instead of a data pipeline that HDFS uses. We use it for both data and metadata. RAFT is, of course, been proven to be correct. Traditionally, RAFT is used only for small updates and transactions. So that fits very well with metadata. However, there's some performance considerations if you are using it also for the data. So what we're doing is we're moving the data as part of the RAFT protocol, but when we write it, we won't write the data in the journal. We will write the data straight on the container storage. Okay, so we write it straight into the files, okay? And so typically, this is configurable, but typically you would want to put a RAFT journal on a separate disk and your data on the other disks. You may want to consider using an SSD for your RAFT disk, okay? And so that's kind of the recommendation, but it'll work with regular disk, and it'll also work with if you are, putting you're sharing your RAFT journal disk with the regular data, okay? And clients will then use a RAFT protocol to write to the data node, okay? There are concepts of open and closed containers, okay? So active writers write only to open containers, and you need at least number of spindles times number of data nodes, open active containers, maybe even multiples of that. Why? Because what you really want is clients to get locality on writes. You don't want to say, I only have 5 open containers. As soon as a container gets full, then I'll move to the next container, I'll move to the next container. You don't want to do that. You have thousands of writers writing. You want to keep all your data nodes, all your spindles busy. You want locality for your writes. You want locality for your reads later on when you read it. Therefore, you want to spread all this around, okay? Container gets closed typically when it's full. That was our original design. Now what we are doing is if it's full and also if we had a failure in the past during the write pipeline, while you were writing, if you had a failure. And so reason was that we would have had to wait while somebody's writing and we failed it, if the quorum goes down, we have to wait for it to get replicated. We had talked to somebody who's worked on the Kudu project, and they said, they went around a similar thing. They also use RAFT. They said, why didn't we just close it? And so we decided to go down that approach. It'll be replicated automatically. And later on, we can open or merge with other closed containers that are small. And we have to kind of do this merge because as data gets deleted from a container, you have a closed container that was full, and then suddenly data gets deleted. It's going to become half full, half empty, right? And so you have to think about merging those and reopening. So do you reopen or do you merge with others? We decided to merge, but that's a longer discussion, okay? And there will be a JIRA on when we make when we do that work in more detail, okay? Little bit of details about Ozone, okay? Itself, there's a master. It also uses a RocksDB, okay? And it talks to the block layer HDDS on the bottom. Client says open, he gets a set of block IDs. He says, get me the block locations. Remember in the past that used to go to the name node. Now it could actually go to the container manager. So one extra RPC hop. But we could cache that on the name node. So as soon as you say open file, collect block IDs, it could give you the locations from that cache. Or could tell you, by the way, here are the cache locations, the rest of it, you go figure it out, or the name node could get it. The Ozone Master could get it. Or we could cache it on the client. So we're going to decide which way to go. It might be more effective just cache it on the client, because then you will have a much more effective cache on each client might be using a different set of blocks, and it just caches it. Okay, so work to be done, some measurements to be made, and then a right choice to be made. Okay, the API. So key looks like volume name, bucket ID, object key. So for example, you could have a volume called home for all the homes, home directories, each user could have a bucket, and you put your files in there, okay? And you call your file foo bar zoo, whatever you want to call it, okay? Those directory names, foo bar and zoo are fake directories. Okay, there's just have a slash in there, just like if you're familiar with Azure or S3, that's what it is. Okay, ACLs at volume and bucket level, future sharding at bucket level. Ozone is consistent, unlike S3. Okay, so you can do rename. If we shard, we will not shard within a bucket, we'll only shard across the bucket. So rename within a bucket will be consistent. That's what our plan is, if you down. Okay, at the bottom, you have an Ozone object API. It's based on the RPC protocol using Hadoop RPC. On top of that, we have a Hadoop compatible file system, Hadoop file context connectors. Okay, very simple connectors. And we'll also have an S3 connector. Okay, so this is to give people who just want to use a straight old S3 API or Azure API directly on this. Okay, this is just interesting to do this. By the way, we have no illusions that HDFS or Ozone will be used on the cloud. Okay, so Bezos can rest easily. We are not trying to compete with him on storage. Not that he would be scared if he did. Okay, we have no illusions because renting EBS or local disk is ridiculously expensive. It doesn't matter which cloud you go to, that if you run a 724 HDFS, you better have a lot of money. Okay, therefore, if you're on the cloud, use S3, use Azure, use Google Cloud Storage. You will want to use HDFS or Ozone FS for caching so that your Hive SQL output goes there on your local stuff, not straight to S3, because S3 is slow, okay? Okay, I better leave some. So where does Ozone Master run? It could run on a separate node with large enough memory, or actually it could even run on the data nodes, okay? And we believe that if you really have a large cluster with thousands of, tens of thousands of clients, you may want to put it, but this is going to be configurable. And storage, our current implementation is using the local disk. In future, we may actually use the container storage itself. We need to think about that a little bit, but it's an option. Okay, an interesting thing that we have built, and then I'll kind of leave it to you, summarize and give you 5 minutes for questions. Something called Quadra. Gives you LUN-like row storage, okay? It can be used for creating mountable disk file system volumes. So for example, if you're using Kubernetes, you'll find this interesting. Okay, so it's a LUN-like storage. The blocks are stored on HDDS. That means it's a reliable distributed storage. Row blocks are those of the native file system, say like ext3. The row block size is dictated by the file system. Okay, in this case, 4K. Row blocks are the unit of I/O operation. They're also the unit of read-write to HDDS, to our new block storage file system. Okay, they share Ozone and Quadra will share HDDS. Okay, current prototype is 1 row block equals to 1 HDDS block. Okay, we really will change this down the road that 1 HDDS blocks is multiple row blocks. But this right now, this was the easiest thing we built. So this one is truly a kind of a prototype. But I had a picture here of, as you can see, it's accessing this. We have a plugin right now that uses JSCSI. That's actually in a separate daemon, but that's kind of dumb because they won't give you the performance because of two RPC hops or 2 I/O network hops. We're going to move that inside as a driver inside the Linux system so that it can talk. You don't have that hop. By the way, if you move it here on the data node side, it would be nice, but you can't because iSCSI doesn't know how to deal with failures of the storage and automatically move around. Okay, but apart from that, there would have been the other option to obviously do that. There is a volume master. I'm going to kind of skip that part and give you some question. Okay, so what's the status? HDFS block we're using, as I said, 2 to 4 gigabytes, and our target scalability of the initial version is to about tens of billions of blocks. For the Ozone Master, our initial target is tens of billions of objects. Down the road, it'll be much larger. Currently, we're trying to stabilize HDDS and Ozone, measure, improve performance, add HA for Ozone Master, and add security. A security design has already been published. Okay, it's been reviewed by some of the key guys who did the design of the original Hadoop security, which was myself, Owen, several others. After GA, further stabilization, further performance improvements will always be ongoing. Add transparent encryption, add erasure codes, add snapshots, or the equivalent that we might do in this new system. Okay, and so HDDS scaling has been proven in real production systems, 4K plus clusters, large amounts of row storage within a customer, within a single thing, with limitation of 500 million files. HDDS+Ozone is we believe, the next solution. It retains some of the good characteristics, like moving computation to storage, horizontal scaling of I/O, petabytes, all this good stuff. We use HDDS, which is block containers, and Ozone, which is a flat namespace. And the community is working on a hierarchical namespace. Take the name node and make it work. Take the old name node and make it work on the new block storage. Okay? So that's kind of thing, and open for questions. Yes, please.
Question of roadmap. So Ozone will be included on HTTP 3?
We are initially going, that was our original plan, but a lot of discussions in the community, so we're going to make that a separate release. We will make sure it releases with the future HTTP release, Hadoop releases, come to HTTP separate, with the Hadoop releases, and there will be like, okay, this version of Ozone works with this version of HDFS, so you can plug it in and put it on the same data nodes. At HortonWorks, we'll also be shipping it in the next release, in HTTP 3.1. Okay, other questions? Yes, please. Say that again, sorry. Yes, there will be an upgrade path. So the question is there an upgrade path? We believe that most customers will be, initially will say, I'm not going to just move my data to Ozone. I need to test it. So they're going to run both systems side by side. They will say, let me run some things on the new one. If it's stable, they might say, now let's copy the data. We have looked at doing what we call a shallow copy, so your data doesn't get copied, but there's a hard link that happens at the low level. Okay, so that's under consideration, but we expect that, as I mentioned, I showed the picture of the two namespaces. We expect that to be the case initially. Later on, we expect customers might say, hey, I'm ready to just say, I used to have HDFS, now I want Ozone, bang, and then we will have an upgrade path for that. Again, we will have to look at doing a shallow copy over there. Or the customer might say, I want, again, even at that time, I want certain data sets to be moved over, because, by the way, you guys don't have encryption right now. I'm using encryption for 3 applications that I'll put on HDFS. But Hadoop deals with multiple namespaces beautifully. Okay, so that's not an issue. Other questions? Yes, please. Yeah, actually, you are right. Actually, you want to be a little bit careful, because you want to go with storage ID. Hadoop right now has a notion of storage ID, but yeah, that's actually a valid point. We should maybe discuss it offline. But that's a valid point. But you need to make sure that if I keep the host name but replace it with some other set of disk, etc., it doesn't get fooled by it. So Hadoop has a notion of a storage ID, okay? And so we have to make sure that part works. But modulo that, you are right. In fact, what we want to do is to make sure that we work with our Ozone Master is not the IP address. It is really by name. So that, especially in the cloud, you have VMs that go away and get replaced. But a very, very, very good point. Anything else? Yes? Sorry?
Can I replace spectrum scale storage
can I scale spectral storage? Oh, you mean row storage? You mean a row storage of IBM or another vendor? Yeah, you should be able to use. If currently you are using a vendor storage directly, a vendor storage, then it should work. But vendors have storage that they sell, and other vendors have vendors of storage, row storage they sell, and they sell file systems. So they already sell a file system that is Hadoop compatible, so issue doesn't work about does it work with that. But if a vendor sells storage that used to work with HDFS, there's no reason why it should not work here. But we could do a deeper dive on that question. Okay, I'm not too familiar with Spectre's storage myself. Other questions? Okay, if there are no questions, let me just, one myth that people have about HDFS is that HDFS does not allow you to scale your storage and compute separately. It's a pain. And by the way, locality doesn't matter. Segregated storage is equally fast, et cetera, et cetera. So this is a big, and there's the myth about Hadoop doesn't. So HDFS and YARN are two separate, okay? It is customary to put compute nodes and data nodes together. You don't have to. You could have a complete separate HDFS with a set of nodes, or you could have a complete set of compute nodes. It works. In fact, it works better than other vendors' segregated storage because you can have rack local locality and kind of use your rack bandwidth. Okay? You can also mix. We have customers who are doing compute and storage together, but have fat nodes that only do storage. So for example, many vendors, HP for example, sells fat nodes that are storage heavy and low CPU. You don't put a compute node on there. You won't put YA there. You can do that. A colleague of mine last week was telling me about he put spinning disk on an HDFS rack that he stripes horizontally, and the compute nodes are compute and storage, but they only have one SSD or two SSDs that are used for local replica. So what happens is he gets much faster writes on data that is hot, that's sitting over there, and then he gets the large volume of this. So for example, that structure is really a very nice structure to have. All of those are possible in HDFS. So it's actually a myth that HDFS forces you to not segregate. You can segregate in a very flexible way, okay? So it's a myth. People who say locality doesn't matter, some vendors probably have solved the speed of light problem. They probably have a private conversation with Einstein. They figured out how to solve it. For us, we find that speed of light is a limitation. We have not had a chance to work with Einstein and solve this problem of speed of light. So we believe that there is a difference between locality has an advantage. But of course, if you have a vendor that has solved the speed of light, by all means, go with them and don't worry about locality, okay? So hope that kind of covers the myth about segregation. We do support it. It is just a matter of configuration. In fact, it's very flexible, okay? Thank you very much. And we are hoping that you guys will try out Ozone one of these days, Ozone and HDDS, okay? We believe this is really the next step in HDFS, and if you're on-prem, this is it. You take this system and you're going to be happy for another 10 years. Okay, thank you.